Okay, so yeah, we're going to start a new chapter on beam deflection. This is chapter 9, and there are several approaches, including one not discussed in the book, but is the methodology behind the beam deflection program. So I said that on Blackboard there are some resources. So I posted these equations. There's something about textbooks, they grow in size to justify the exorbitant price that you have to pay. And I need to deconstruct, that is, distill the essence out of a chapter of 100 pages to make it digestible. But yeah, the subject is very relevant because there are instances where deflection is a limiting factor in application. So mechanical engineering, you have, or maybe let's start with more like everyday life if you want. And we looked at this or discussed this briefly earlier. So if you have like a second floor in a building, and as you step, you feel the floor sagging under your weight, even if nothing happens, that's unsettling. You then have the very tall buildings, and under the effect of the wind, excluding earthquakes, so under the effect of wind, they can swing, right? And I think all of them now have tune mass dampers. Okay, so wind blows, the top swings. You have your office at the 100th floor. That's pretty, you get seasick or motion sickness. So they are what are called tune mass dampers. And as you know, everybody's been on a swing, right? If not, you can visit a park and you can go on a swing, and you can use just your lower legs. You swing them, and if you time it right, the swing will start swing with you, right? But you can also stop the swing from swinging by changing timing. So likewise, you move your lower leg such that the oscillation is reduced. So it's the same with the tune mass dampers. They are assembled of concrete slabs, and some are suspended on cables, some are floated on hydrostatic bearing, pneumatic bearings, and they're actuators that sense the motion of the building, and they move that mass on top the right way, the opposite, and you can dampen the oscillation. But the first effect, that is the deflection of you can think of a building like a cantilever, right? So yeah, a cantilever or a building, and deflection at the top is something that you want to limit under the effect of, like I said, wind forces. And then I said machine design problems. There are many where you want to limit the deflection. You have shafts, say 2 parallel shafts with gears mounted to them, and maybe there are belts and sheaves in tension. And if the shaft deflects, again, we discussed this, if you have 2 gears meshing, and if the shaft deflect, and if they stay parallel to their planes, the gears is not as bad, but you can also have, if it's on a side, or you can have rotation, and the gears, instead of meshing nicely on the width of their teeth, they start meshing on a side, and that's increased contact stress and accelerated wear, and you don't want that to happen. So there are recommendations. They're repeated here, like how much deflection per foot or per inch in a structure for various applications. Okay, so the study of deflection, that will be again just from an unloaded, perfectly straight configuration under the effect of load, and what I'm doing it now, I'm applying 2 end moments, okay, or 2 end moments. So one is how far points on a beam moved from the original straight line position, and then you also care, in consideration of the gears meshing, you care about the change of slope. That is, slope is the angle made with the horizontal of the tangent. So if I have the, I'm trying to just one person show, so I'm trying to, this being the tangent, you can see, so I'm moving it, sliding along. I slide it along, so it's tangent. It's a smooth curve of the beam, and I slide along, and you can see here it's horizontal, remains parallel to the original axis of the beam, but then elsewhere it goes from, as you look at the my contraption here, so you see what? You see a negative slope, and then you see a positive slope, okay? So, and those are likewise or could be important. And there's their relationship that go, we looked at some of them, but they're a series of differential relation and integral. You can go the other way, that relate on what? Load. It says load intensity. Essentially, this is distributed load. Okay, so it relates all the way to deflection, and this is a fourth order derivative. And you can see the type of material, the stiffness of the material being present. So it's one thing to have a titanium, say, which has a lower Young's modulus, and the other is to have steel or maybe carbide. We discussed about this too. You have, you go to the machine shop, and your tool holders, like boarding bars, they're made of carbide, which has a higher Young's modulus of elasticity than ordinary steel. Okay, so this is distributed load. This is shear. So we have the third derivative of this deflection. And again, how do you measure deflection? You have x along the beam, and you call deflection the y displacement of any point on the neutral axis of the beam. So we're analyzing the displacement, the deflection essentially, and slope of the curve that connects the centroids along the beam. And by the way, the moment of inertia of the beam can change. If you look at the homework problem, the very lower, some of them have different moments of inertia. They're the beam, they're fabricated, have a section usually in the middle. You increase this term, so this term can vary. You can even have I changing along the beam. So if you have like a middle section that is one material, and then you weld to it, you brace to it, different material, although that's less likely, less common. But yeah, you can have the original rectangular bar, and you clad it above and below with copper. It's steel originally put copper above and below. So it's something not as discussed, but you'll have a change. You will have a change, and it will be like an average. Then you need to figure out, and the book does not discuss. I don't know how to do that. First time I'm actually dropping this in where you can have the similar material. But this is very common. So stepped shafts, fabricated beams, and you see this commonly with areas that were reinforced. You have a plate that you welded where loads are applied to help with delivering of the load in that location. But you also add to the geometric stiffness of the beam. And then bending moment. Second derivative of this deflection, slope at any point on the centroidal line, the neutral axis of the beam. Again, points connecting the centroids along the beam will be in measure from the straight undeflected. That's the deflection, and then the slope will be time derivative. You know this very well. You have a curve in 2D. The slope is going to be the time derivative of, so if you have a curve y of x, the slope of the tangent at any point is going to be dy over dx. You know this from calculus, right? Okay. All right, so these are the equations. They're showing the derivative form, but you can of course go in, you can go the other way. So you can, for example, and we did this. We took the derivative of we're stating that dm, what was it? dm over dx was v of x. Okay, and we use area method. We apply this constantly, area method. We also know that v over dx, it's distributed load. We apply that a few times also. Okay, so these are the main equation. It's Euler-Bernoulli model of a beam for long, slender, long beams. Yes. One assumption that is made in all these theories that as you deflect the beam, okay, you deflect the beam under load, and if you slice through, the section remains perpendicular to the neutral axis. So essentially, the cross section rotates with the beam, does not lag behind. Okay, so going to the text. We have the book discusses a number of or a few approaches to analyze beam deflection, and we'll look at hopefully even do some problems on what is called formula method. Okay, so it shows here a simply supported beam with two supports at the very end, right? And it's loaded with two loads in the middle, and it shows the shape of the deflected beam. I think we even looked at this. So a smiling beam, it deflects and it smiles. We're expecting a positive moment. And by the way, the deflection is considered positive if with y-axis down. And then if you have an overhang like you see here, so simply supported with an overhang, and you have the load, this would be the shape of the deflected beam. It's a smooth curve, yes, and it will be, depends on the load application, where they are positioned. Here I have the case from above where I added a load in between the supports, and you can see how if this is big enough, it can reverse the trend of the free end and will move up. And other instances. So we have, as you can see here, I have just one load. Here I have two loads. You can assume this, and this is something that will be used called principal superposition. So if we have equations, canned equations, that allows us to analyze this instance, and we have another load, we can assume essentially that this case is an overlap of two cases of this type with a single load off from the center, okay? I can even, for convenience, I may even mirror, that is, look at the problem from behind if it makes sense. Okay, so yeah, simply supported beams. And then we have what? We have the cantilever. It's a fixed end. And something that I should mention at this point. So we have the tangent to the beam. Let's say this extends. Do I have, no, well, was another one mirrored. But yeah, you have the tangent, which follows. The tangent is 0 here, and it goes to a negative value coming from a positive. But it starts here at the support with a non-zero slope, the tangent to the curve, okay? If you have a cantilever, because of the way the support acts, the beam right at the support has a 0 slope, and as you move away, the slope increases in the negative sense. Does it make sense? So it matters. If I have supports, then the deflection is 0. Here, both the slope and deflection is 0. And these are important because as we integrate, we need to reconcile some constants of integration. And how do you do that? By taking into account what are called initial conditions or boundary conditions, okay? So yeah, even initial, that is, you say x equals 0. But if you have a support if I have an overhang also to the left, then location where deflection is 0 does not coincide with y0. But again, I'm using that information, that additional information, to complete some analysis. That is some equations that are needed in solving this problem with using the equation projected earlier through calculus. Okay, so this is a cantilever beam that has two loads. One before at the end, W1 pointing down, and one here below. I can assume, same as I said here, so I have just one load and then two loads. I can assume that a case like this one is an overlap of a load at the end and then another load that is by itself elsewhere. And essentially, if you draw the deflected beam in two instances and then you add deflection by deflection with the corresponding deflection along the beam in multiple locations, if you work to work this graphically, you get the final deflection result of combination of the two loads, as we'll be doing in this chapter for some of the problems. Okay, we can have statically undetermined beams. This is a continuous beam, it's called, when you have multiple supports. Using principal superposition and knowledge of deflection of the beams with just two supports, you can come in. So if I have, say, well, here there are four, but if I have just two supports, okay, and I'm assuming it was the live load, okay, and if I'm assuming additional loads that are unknown as magnitude, but I manipulate them until the deflection where the two additional supports are go to 0, then I am capturing this statically undetermined case using simply supported cases. Does it make sense? So if I have a, let me explain. So if I have a what? How can you induce some load to this? Maybe professor improvising, like jazz. You play jazz. So we have a beam that's loaded. You can say this is, well, it's more to it because I'm also stiffening it here. But I have what? I have a free end that drop below its original location. Now, if I'm applying a force at the end until, modulate, until the deflection where my finger is goes back to 0, I can model this as a support, what is called a supported cantilever. Okay, supported cantilevers are this kind of arrangements. Okay, so without the supporting column, it was just a cantilever, I bring the support in place and I reduce this deflection to 0. Does it make sense? Do you follow, or are you doing other things? I'm seeing everybody absorbed by their laptops. How do you follow the text? You're trying, because there are too many pages. I'm just, I'm introducing the concepts, and then you'll see the essence is doing exercises, okay? So page 505 repeats some recommendations on how big deflection should be. We saw these, or equivalent to these, in early chapter for torsional deflection. The deflection analysis, I mentioned the case of buildings or shafts, but it's also used. There are ways to estimate what is called resonant frequency or critical speed of shafts, or could be of beams too. If you have a tall building, it may have its own or has its own natural frequency. All right, and but this is more the case with, and you can have self-induced vibration. Tacoma Narrows Bridge, maybe you're familiar. In the 40s, they built a bridge and they had like the sides, as the wind was blowing, certain speed, not a high speed, like 30-something miles per hour. The turbulence created beyond the guards produced a large amplitude oscillation to the bridge, and in a few months collapsed. That was documented on camera. So yeah, and although that was a complex case, but in talking about shafts now, so you have a rotating shaft, and nothing is perfect in nature. You know, if it were, you could, I mean, just because of its own deflection on its own weight, you have the center mass that goes slightly off alignment with the support. So there are speeds at which, you know, the oscillation is that is the deflection of the shaft as it rotates reach a maximum, and those can be dangerous in the sense that they overload the bearings, and the large deflection can even cause failure, permanent deformation failure of the shaft. Machinery is designed to operate either below the critical speed or above. If they operate above the critical speed, and that will be the case of jet engine. Jet engine or gas turbines, the smaller ones in particular, they run very fast, like tens of thousands of RPM. And you accelerate quickly past and there are multiple critical speeds, by the way. The first critical speed, and then operating happens above it, and you stay away from large amplitudes that can damage the bearings and the rotor itself. So yeah, critical speed of shafts can be calculated, and in general of supported beams can be calculated knowing deflection. Okay, so here's an arrangement showing something that we know already, the load, shear, force, and bending moment diagram. And then two more diagrams here. So you have the slope, and then you have the deflection, all right? And we have what? We have, we know where the shear is zero at the moment it goes to a maximum, or could be there is a local extrema, it's called. So here's a maximum, but if I reverse, I put P acting from below, this will flip, and this will be a minimum actually. And then we talk primarily deflection. Yeah, so you have you have supports at the end. I said that deflection of the supports is zero. Supports allow rotation of the beam, so we have a slope that is non-zero at the ends. Okay, and the slope goes from a negative to a positive value, as shown here. So where the tangent to the neutral axis of the beam, the deflected beam, is zero, I have a maximum deflection. Again, something that things that we know from calculus. Okay, so it's straightforward. Again, we know from math. So if you have the equation y of x, slope is going to be nothing but the dy over dx. It gets you the slope. But then a relationship between moment and slope, and so how do we bring this in? It has to do with the loading and the moment distribution, and also has to do with the stiffness of the material. We saw the equation earlier from a different source, and the geometric stiffness. Okay, so in the derivation of the equations that are on Blackboard, we're going to make use of the radius of curvature and curvature, that is, of the deflected beam. So we're going to delimit a piece of the beam, show it in the deflected mode, arched, that is, will be a radius. Locally you can approximate that deflect with an arch of circle. The radius of the arch of circle is the radius of curvature. 1 over r is k, the radius of curvature, or the curvature, I'm sorry. So radius curvature has units of length. Curvature is inverse of radius of curvature, units of length at -1. Okay, and so again, we move along the beam. We have variation in x and y, infinitesimal variation x and y. There's a way you can relate the equation of y of x to the radius of curvature. You saw this in other classes. We keep on saying slope theta, but for small angles, which is our case, beam don't deflect dramatically in our analysis, just slightly. So you can approximate tangent of the angle with the angle in radians. You've done this before, their approximation, you say. And we can do likewise sine approximately theta, the first order approximation. Okay. So yeah, this is was that approximation stated. Okay, formula method. So the first approach that we'll learn how to handle beam deflection is using formula method. So for this, we're going to go to the appendix. Let's see, where are you, appendix? So it says beam deflection formula simply supported beam deflection formula, cantilever, beam deflection formula, statically indeterminate beams. So let's look at them and see how it can make use. So this would be the very first one, A, lowercase a. It's a supported beam with a load P in the middle. Okay, and it allows us to. So it says deflection maximum is deflection at B and has this magnitude. So it depends, of course, on P. The bigger the span, the more deflection. It holds to reason. You have and then material stiffness and geometric stiffness will reduce this deflection, right? And then it says the equation. So you look at this as y of x. And it says between A and B. So you have between A and B, the equation of the deflected beam would be this one. Okay, does not give us a slope equation. Other textbooks, they have more information with each entry. But if you want, if for example, I'm asking what's the slope, say this is a shaft with gear and the gear is mounted, say, has to be where load is. How would you get the slope? You just take the derivative of y with respect to x, and that gets you the slope. So maybe that's why they haven't included them. Again, theta won't be anything but, or nothing but dy over dx. And that function y of x is this one. Okay. Also note how axes are oriented. So origin, x along to the right, and y up. I think I said y down, but it's y up. Okay, then we move to B. And then we see what? Firstly, that A is greater than B. There's an overhang. Load is no longer in the middle. And you can see here an x1. And then you see the x. And there's a V. So read carefully the what is provided. And then it says maximum deflection. If you're interested in maximum deflection of the beam, you look at this, and it says where it is, x, y. So if you know P, A, and B, length L, you can calculate, and of course, material, area, moment of inertia, you can calculate maximum deflection. It tells you where it happens at x1. Deflection of the load also can be of concern, and you evaluate it with the other equation. Does it make sense? And then equation of the beam. It says between A and B, the longer segment. Between A and B would be this equation. Between B and C, the short segment would be this one. And note now that I have y as function of a new variable. So x was changed to this new variable. Does it make sense? So you need to pay attention. If I'm to go back to this first one, and if I want the equation between C and B, it will be this same equation, but replacing x with a V that's measured from C towards A. Like defining a new variable. We're looking at the problem from behind. You draw it on a piece of glass and you look from behind. Does it make sense? You go to one of the main entrances where we have glass doors, you draw this figure, but then you come back and you look from the other side, and now, X is here. And then it says, do we have an equation between C and D? So A and B, actually this is trivial. If it looks curved, it's not correct. So between C and D, this is just a straight line and does not seem to be one. Does it make sense? Because if I have a beam and I load it here from the support to the free end, there's no loading and the beam just remains straight following the slope evaluated at point C. Okay, so if I'm asking you, if somebody asks you, write me the equation of the line that goes between C and D, that will just be an equation of a line with a slope that's going to be equal to what? The slope of the beam immediately left the point C. So you get that by taking derivative with respect to V of this equation, and then you go ahead and use it to state the equation of the beam. Again, no load, no deflection, but the beam followed this other section and continues straight. This is a particular case of loading where we have two equal forces acting to the inside that's simply supported at equal distance. This would be a case of pure bending between the loads that is between B and C, right? And it tells us where the maximum deflection happens. It's at the middle because of the symmetry of loading. What the deflection of the loads is, y of B and C, right there. And then the equation of the beam between A and B would be this equation. Between B and C would be this equation, uses X. I don't have what Greek symbol is this? Is it eta? I always have them wrong. There's in my office a table with Greek letters, but never managed to memorize. All right, uniformly distributed load over the full length. And you'd expect maximum deflection to be in the middle. It is. And the equation of the neutral axis, deflected neutral axis, you have it here. And deflection at point C, okay, if you know this distance, again, this continues as a straight line, and the deflection at D would be calculated with this formula. And we can actually derive this because let's see, if you're to evaluate a slope that is delta at C, you take derivative of y, it says between A and B. So the slope at A is the slope at C. So you evaluate it and you make x equals 0. So what does it get you? Would be derivative of this, and these go to 0, so it'll be WL324EI, right? And then times A. So yeah, we were able to quickly prove where this last equation for entry D came from. All right, in other cases, again, read carefully, look at notations, and here do we have does it say between A and B, between B and C, does not tell us where the maximum deflection is. And if it doesn't, then you would have to either look up more detailed information about this kind of loading, or you evaluate the derivative and set it to 0. That gets you, if you calculate the solution to dy over dx equals 0, and that gives you x at the maximum deflection, evaluate y at the respective x. A moment, concentrated moment on a supported beam. So N supports a concentrated moment. and it tells us the equation of y, but doesn't tell us what the maximum deflections are. So again, you'd have to, if it's of interest, to calculate them explicit or using the method that I just said. And a supported beam with an overhang and the load at the overhang. This is what? Uniformly distributed load with equal overhangs. Again, maximum deflection is not given, just the equation of the beam. Have we seen this before? Oh, okay, 2 overhangs, symmetric supports here, equation of the beam, distributed load at an overhang, and then cantilever beams. So cantilevers with a load at the end, with a load inward, not at the very end. Again, from B to C, the beam remains straight, which does not quite look straight on their figure. And then if I have an cantilever with distributed load, again, here and earlier, we have maximum deflection. A moment at the end on a cantilever. And now we have a few cases of statically undetermined beams. As you can see there, so I'm on page, what page is this? 805. So this is a supported cantilever. It's called, and it gives us also the shear force and bending moment diagrams, which is superfluous because all we need to know is just what the reactions are, and then we can draw the diagram. Do you agree? So this is, to us, is superfluous. Once you know what the reactions of the supports are, you analyze it like a statically determined beam. So this is we know this is the jump by 11 over 16 of P. P is half distance between the free end and the where the support is, and then the drop by P and ends with yes. And then for the moment, what is MA? Does it say MA? Okay, it shows here. This is a typo. This should have been like a subscript, but we have MA on this diagram. They could have placed it here, and no need for these really. So once you know the moment, the reaction moment of the support, and you can draw the diagram. Okay, so the value here, 5 PL over 32 is nothing but negative 3 PL over 16 plus 11 over 16 P times L over 2. Okay, you'll see what I anticipated that you can analyze this using principle of superpositions as being the overlap between 2 statically determined cases. So we have this case and this case overlapped, where this force is negative P, or acting. Of course, the 2 are different. You can imagine, you do principle superposition, you have 2 different P's. You don't mix notation. There will be 2 separate cases. So I make this negative and then calculate the deflection for the individual cases. One will be down, one will be up. Same amount, but with a plus. And then I said this equals this, and it gets me what? It gets me this force due to the support of the cantilever, if it makes sense. All right. There are other ways, other means of deriving the reactions of support. So again, this is supported cantilever, statically indeterminate, but we can assume it as an overlap or principal superposition of 2 cases. Here's a supported cantilever with a load. So was it special over the earlier one? I have So A before I think was in the middle. Yes, was in the middle here. A and B are different. Before A and B were L over 2. Yes. And instead of writing them straight on the drawing, MA, RA, and RC, they are here. And then it shows the, like readily available, what the moment, what will be the maximum, could be less than this one though, at where shear goes through 0. Okay, and deflections at the loads between A and B equation. So this is specific to location. This is a function of y, and likewise function of y between B and C, the rest of the beam. Okay, more statically determined case. So supported cantilever was a distributed load, and then we have what the supported cantilever was an overhang. So if you see an arrow that has this transverse little line, it means a support. So you have a supported cantilever over an overhang. Tells us the moment at the support, maximum moment here. Okay. So again, read carefully what the these appendices, the various entries offer, and make use of it. This one is another case of statically indeterminate. This is a double supported beam, as you can see. So it's an incastration here. It's another incastration with a load in the middle. The magnitude of the reactions of the supports and the moments at the supports, they are equal, and then also equal to the moment at the load, again, due to symmetry, PL over 8. And then one like the entry E, but we have a load that is other than cent or in the middle of the beam. And then let's see what else. I think there's one with 3 support. No, distributed load, and distributed load over double supported beam, and then distributed load, uniformly distributed load over a continuous beam that is with 3 supports. Okay, 1, 2, 3 supports, and then with 4 supports, likewise a statically indeterminate beam, and 1, 2, 3, 4, 5 supports on a uniformly distributed load. And this is it. So for superposition using deflection formula, I anticipate, or gave an example how you can combine them as formula method. The book continues. It shows some comparison if you're to going in all the details in the other book that I'm using by the same first author, different co-authors. He's likewise comparing simply supported beams with cantilevers, and then supported cantilever and double supported beams or fixed end beams. And as you can see, for the cantilever, it takes just 1/2 length. In any case, maximum deflection occurs for the cantilever, minimum deflection occurs for the fixed end beam. Why is that? Because you limit rotation, or that the slope is limited to 0 and 0 at the support. On the supported cantilever, slope is 0 here, but it is allowed to change. Relevant information if you design with beam and you want to minimize deflection. Again, the overhanging or the cantilevers are not good when it comes to deflection, by far, you can see here. So everything else is like 1/2, quarter, and 1/8. Okay. There are ways of mitigating deflection other than changing the type of supporting. One is to, how can you limit deflection? By just looking here. So, well, maybe looking at the equations, and we can go back in the formula method in the appendix. We can go back. You always see L going at power 3 and it's above, right? Or power 2 maybe, and other multipliers. So shorter beams will deflect less. And then you can work with the area property. That's why the I-beams were devised, and we recognize that a flat rectangle is flexible, but if I rotate 90 degrees, much stiffer. And then, of course, the ultimate last resort, you can change to a more stiffer material. And I gave you the example of boring bars used on machine tools, on milling machines and boring mills. Okay. And then superposition was examples shown how you can analyze statically indeterminate beams. The same that I was telling you about with reference to the appendices. So you take overlap of two cases. Cantilever was a cantilever or supporting cantilever. You have a load, and then you have you add another force acting at the end from below. So in the early equation or the equations from the deflection in the appendix, you make a P negative P, and then you set this deflection and this one deflection. You set them equal. Well, one will be negative, the other one will be positive, and you solve for R B. That's enough for you to now calculate what I was rather shear force and bending moment diagram. Deflection elsewhere is going to be, again, I once you figure out RB and this become equal to this one, deflection elsewhere will be, so for example, at the location that is 2/3 from A, so just add this deflection to this deflection or their signs, and the sum would be the net deflection at that point. Okay. Successive integration method. So over a course of 2.5 pages, they derived the equation. If we go back to, they derived this equation. What was it? This one with the notation for theta. So notation for theta introduced here. So relating moment to the deflection and to the slope. So this, from where I've got this information, this condensed set of equations, it uses delta instead of y for deflection. We used y. And theta likewise, actually no, this our book uses delta for deflection. It might be a little bit confusing. I'm going to edit these equations and reload them on Blackboard. So there's a bit of a course of 2 pages explaining how that was developed. So you start with the limit, that short piece of the beam before it's loaded, and then after loading it curves, ends, cross sections rotate with the neutral axis. So really, if you're to measure an angle between the tangent at this point and the transverse section, this will be 90 degrees. And likewise here, if I take the angle between the tangent at the other end of the short piece of the originally long beam, this likewise is going to be 90 degrees. Because the end plane, sections rotate, I have this angle d theta, and it's also going to be an angle that is measured if I take, I take this plane, translate it, and then measure relative to the rotated end. That's also d theta. A C that will be used was flexure formula, and then we have the radius of curvature. Radius of curvature can be related to y of x equation of the neutral axis of the beam, the way was was explaining calculus. So the piece of the beam now, as it was original and rotated, but allowing the length of each fiber, in a sense, to remain constant length, which doesn't happen because of the the effect here. So we have compression on top, maximum stretch below. So you need to relate what? We need to relate this small deflection to the stresses developed in the beam and ultimately to the flexure formula. So again, equation for the radius of curvature, flexure formula, and some geometry. So this deflection delta, the stretch of this beam, which is equal to compression here if C equals C. So what is this equal to? This is going to be C times d theta. This little piece is C times d theta. Okay, and so flexure formula was brought in at some point. Definition for stress and strain, Hooke's law. Epsilon is sigma E, epsilon being nothing but delta. Delta is epsilon over initial length. So let's see what's epsilon. So epsilon would be initial length dx, and it goes to dx plus this delta, and delta we said is d theta times c. So all combined together, the way the book shows, again, flexure formula that we know. There's a little bit of misleading here. This is not it appears to be like an index, which is not. It's just a multiplier. So flexure formula, we introduce strain from Hooke's law, and strain as function of deflection as function of c and a rotation angle. And we take 1 over r, which is the curvature. And curvature now is, from calculus, is second derivative of equation of the curve with respect to x. If you have a function, 2D graph that says y of x, curvature 1 over r at any point is this guy, and then ultimately you combine them, and we have this. I think it's called Euler's formula, right? So you relate what? Moment applies stiffness of the material, stiffness of the cross section, to the what would be the second derivative of the equation of the neutral axis of the beam. And you isolate m. In m, again, it's related to, as I said, plus this term separated. And you could go in instances. So, for example, you can say the first derivative is something that is done. So the first derivative of y with respect to theta, so you say that is slope. So say you can write also this one as d over dx of theta, and you can integrate in order to get from m, so integrate over m to get the slope. And then you integrate from the slope, is the way we're going to do. You integrate from the slope to go to deflection, if that's the one that's or usually ultimately we're interested in. So here are examples. I said that you're what? You're dy. So here going like this one is theta. So you see theta here, and integral from it could be the end of the beam where x is 0 to a current x, and so a bit earlier introduces the discussion is about the constant of integrations and constant of integration that need to be reconciled from boundary conditions or limit conditions. Okay. The chapter continues again with examples. We're going to do some a bit more, the easier ones are, in terms of reconciling concept of integrations, are the cantilevers. Why is that? Because we know that at x equals 0, both the slope and the deflection are 0. That makes it easy. Less straightforward when you have a beam that starts with an overhang. There you have deflection and slope unknown. If it's a supported beam and the 0 is at a support, you at least know why that is 0. You can have shafts that are stepped or fabricated beams where moment of inertia changes along the beam. So you start with x0 going to full length. So it's one moment of inertia here, different one. Looks like come back to the original one. Yeah, that need to be accounted. So you, without going into details, the book makes this as a separate class of problems. But really is it's just a matter of working with like piecewise continuous function and integrate over separate intervals corresponding to the different I values over there. Okay. All right, so let's go into some problems. And first we're going to do statically determined cases for which we have readily available formula that is using formula method. And I'm going to raise this, the screen, and we'll look at problem 9.7. In the reference book for the FE exam, you have a tabulated deflection formula. Okay. Let's see, paint. I'm going to grab, will be 7 for now. Do also 11, so rectangle. Let's do, I said 7 and 11. 7, 11. This is a chain of convenience stores. 7-Eleven. I think it is. Over in your area. I haven't seen them here. Okay, copy. Select all. Paste. Come back to this. Let me introduce you to these resources here. So we're going to use these two. I've seen Beam Guru used by students. There's just a link. It's online. There are others. The book actually has several. 1, 2, 3, 4, 5, 6 was the reference. It said internet sites. So here he added the length. So beam length 8 was 10 meters, centimeters, inch, meters, forces, kilonewtons, newtons, whatever. And then supports. This is beam. This does only moment diagram. Have you tried Beam Guru? Trying to or now. So it says on the left, on the right, or at the position. So I put it on the position. It could be. I think we can make it 1 meter to the. Oh, it went all the way to the other end. 0.1. I think I changed. What was the length? 1 meter. Okay, need to remember. And add. And then I have this other one. It's our sliding support. So this would be on the right or at position at say 0.9 or 8.5, let's say. Add. And then I have loads and an assortment of what? Forces, and it could be an angle, moments, distributed loads, constantly distributed or linearly distributed loads. So I can put a constant force straight down, and the position would be like, say, 0.4 in magnitude, let's say 100. And if I put a minus in front, it flips. And I add it, and then another load. Let's make it so start position. It can start at 0, goes all the way to 1. I'm sorry, 1. And then starts with 10 and goes to 100. And well, I need to make the numbers negative, it can cross 50 and 100 or 500. Make it more dramatic. Not even. So 500, 150. 50 says. Okay, add and then calculate. Calculate. And yeah, these are the shear force and bending moment diagrams. Let's see. Beam parameters. Calculate, what does it say? Bending, shear force, axial force, reverse bending moment diagram convention, cross-section optimization, select cross-section, full hand calculation. So this is just for shear force and bending moment diagram. And I was telling you, I saw this on some capstone presentations, and I remember it's Beam Guru. So yeah, you may use this quickly to verify work. Of course, you cannot do it at an exam. There is a beam calculator, and this beam, I'm verifying like right now. If I copied, edit, copy, and go to downloads, what is it? Linux, this PC, documents, and I say paste. All right. You have to have this an image with the name Splash. If you don't, it doesn't work. Otherwise, you just launch it, and it says, don't run or run. Oh. Where if I say don't run, but what if I want to run it? Where it says more info? Run anyway. Okay, thank you. I was about to say, yeah, welcome to the 21st century. This came as an additional or supplementary resource, was the book, the previous edition, up to the previous edition of the book. Jack Zecker, I think he retired, professor, and over there they had an option. You can make a career as an university professor doing educational type stuff, and it looks like he chose that. And one of his contribution is the beam calculator. I cannot do that. You either do hardcore research or you call yourself a professional track. And there are other names. A clinical professor, non-research guy. Okay. But yeah, this is what he prepared, and it says intended for education purpose. All right. So units. Start with units. This uses finite elements for beam analysis, and it does deflection. So you can go with meters, and then beam properties, beam length in meters. I think we had one earlier. And then modulus of elasticity, gigapascals. This would be like for steel. Moment of inertia. So you'd need to know moment of inertia. We stay with 1,000. Again, you know the I-beam, say, section. You go to the end of the book, extract moment of inertia from there. Okay, we say it was 1,000. Although I could can do more specific examples. And then it says enter distance from NA to top, the C values. If you remember, it said C top and there will be a C bottom. We leave them as default, and then C bottom. And now we need to put the support. So it allows for statically indeterminate cases. So you can add, you can have pinned without sliding, or you can have a fixed end, and so you can do a supported cantilever. So fixed end and add, and it goes at 0. And then, well, I said supported cantilever. So there will be with a roller, add, and at the distance at the other end. Okay, so now I have a supported cantilever. This is not the statically determined case. And then we add loads. So concentrated, distributed, or a moment. So distributed, I add a distributed load, and it starts, let's say, from point 1, goes to point 8 of the beam. And then magnitude at starts, the start could be 10 Newton per meter distributed load. And let's say it goes to 50. And we have a distributed load. I can add a concentrated force, add, could be in the middle, port 5. And magnitude, make it significant. Oh, you know what I did? There's a disproportion of size between the distributed and the concentrated. I think there are ways to which you can edit. And let's do analyze. Looks like I can modify, delete. Okay, so I deleted, add a concentrated force. It was too big earlier, so it's at 0.5. And then magnitude, let's make it 100 newtons. Okay, and analyze. So shear diagram, and you need to select on the diagram. So you click and it tells you the values. Each line corresponds to one node, so you can even tell how many nodes has his finite element model. So it'll be 1, 2, 3, 4, 5, whatever. And then you press escape and it generates for you the moment diagram. So you can click and it tells you the magnitude of the moments. You see updates that message. Escape and then deflection. So I have deflection of the beam as expected, since this is supported and no slope. And then maximum. It says maximum deflection at 0.56 meters, right? And let's see. As you can see, you cannot click anywhere. It just goes takes you to where the nodes are. And then we have deflection, but we don't have stress. This is, we never created this kind of diagrams, but since the area properties were given, you just essentially use, it's a figure similar to the moment diagram, multiplied by C over I or divided by S section modules. You all try to use these resources. Okay. I believe, let me say, do I ask you to calculate a slope given for Zekker's program? Okay, so numerical derivation generate the slope diagram of the two beams. So since the slope diagram is not given explicitly, so I need to use the deflection now. And if I say save as, hopefully you went somewhere. Save as. So let's see. Yes. So I just took this one and how do you open this with Notepad? Open with. More apps. Okay, more apps. Okay. All right, so you're looking here at what? At the computed displacement. X displacement, Y displacement. I said Z rotation. And then there are forces. So the graph of interest is this one, has 51 nodes. So copy. And we go to Excel. So you'll probably go to Excel, blank work note, and paste. And let's see what we have here. So node, X, Y, and rotation. So let's go and say, I'm sure if you've done this before. So data, does it say text to column? Yes. And delimited by comma. Okay, so I can say, and here, text to column and delimited by space. I don't care much about the node. Let me see what rotation is. So if I select this column, you don't remember what rotation is. Maybe it might just be the slope. So data, where is it? Charts. Insert charts, and all charts. Where is it? I want one of these. Come on. So insert. I need to sit and look from the, like I'll do it on my own computer because it's a all charts scattered, and this one here. Why it looks different than the one that I confirm? Good grief. Insert, I say, sorry for this. Should have tried it in my office. And we'll have this, and OK, and OK. It does not make sense to me. What's wrong? Oh, x displacement at 0. Well, I can make it as function of the nodes. Let's look again. So if I'm to x, y, x is, it might be an issue with the round off. So it rounded to just in the export table. Might be a glitch in this program. So everything was less than 1 and it rounded to zeros, but this is the x-axis. You can go from nodes, they're equally spaced, you know the full length is 1, we can recreate the x value. Does it make sense? So I can, the true displacement, well, it's 0. So if we have 51, 50 was 1 meter, so I'll say equals 1 over 50. If you have 51 points, you have 50 intervals. And then the second one is going to be what? This times, we said 1 over 50. And I think, you think you will take care of the zeros? Okay, if you look here, the x displacement, it's all 0. So the original data is flawed. It's first time I'm seeing it. So what was it? This times. So the problem was with Zecker, not with Excel. And I said L, and L was 1. Okay, going all the way to the bottom. That's why the issue, I didn't realize. If you work with other units like millimeters, now I have units of length, okay? And this is plot of z rotation. So the z rotation is the displacement. But this will be on camera, and you can see. So let's evaluate dy over dx, okay? Have you heard of finite differences? I'm going to apply finite differences, not calculate the slope. Let's compare with what he calls z rotation if it's indeed our slope. So theta is dy over dx. And I'm going to use, I said, finite difference. So, and that will be centered differences. So I'm not starting from with the very first. And that's going to be essentially ascent divided by displacement. So I go with next minus previous of y divided by the corresponding x displacement, this minus this. Okay? Does it make sense what I did? So if you have on a graph, if you have 3 points, so there will be xi plus 1, xi plus 2. I can, and this is, be y I plus 1, yi plus 2. That's a 2. Then dy over dx at the location I plus 1, the middle point, it's approximated as yi plus 2 minus yi minus I period over xi plus 2 minus I. It's what I did. If you look at a graph, it would be like what? So what is the slope? This piece dy over dx. dy over dx. Say dy. Delta. Okay, delta. Sorry. Is it clear? All right, so let's see what we get. So I expand this all the way down. The last one is not I'm going to do backward difference. Just watch here. So it's very easy. I'm just dragging these cells back in place. And then this one, copy, I paste. There will be not a number. Paste, I said. But if I drag these, this will be 4 differences. The other one was backward differences for. Okay, so let's see. If instead we look at this, does it change the graph? No. So what I thought is missing, but what he calls z-rotation is the actual deflection. He does not, in the program, does not generate the graph, but is available. You can get it exported. So whether you wanted to do the way I just explained, or just use the z-rotation, that'll be the slope. However, this appears to be an issue when receiving from his program the x values when you due to the round off, it's cutting to no decimal. Okay, so that was one. And then we need to go do successive integration. That will happen tomorrow. I'll introduce you to the spreadsheet. So the spreadsheet. The spreadsheet here where it says beam calculator, no, this is Zachers again. This one. This is something I did. Open file. You see some instructions here. Copy. And I go to, it's a copy. And then we go to download this PC, documents, paste. And English or SI, so let's go to English. All right, so it says enable editing. You can have a cantilever, or you can have a simple beam, simply supported beam. You describe the beam, we'll come back to this, as on rows, and you can add labels to the rows. We'll do an example. So section, and how many integration points? I think there are a few hundred. All right. So it says edit what's in red only. So length of the beam. It uses the 500 points, evaluates a step, populates this column. You see length over 400. Do you know how to label cells and refer them with names other than, say, H4? You can. So if I want to call this right now, it's named E5. But I can call this Tuesday. I can call it Tuesday. I can refer to it as Tuesday. You know this? So you go to formulas, name manager, And there's and you can have multiple names for the same cell. This is very easy to debug equations. 10 times easier than just say, you carry or like a alias table. Does it make sense? Instead of going with $, you froze the cell. So you will see this if you inspect the cell a little. Anyway, so you have X along the beam. I can label sections B, C, D. Of course, you need to, you could add rows in between. And I can add distributed loads. So if it's constant, I'm just going to add. If I want to add distributed loads, it will be negative, foot per, we're working in pounds and foot. So 10 negative, we went to negative. I said negative 10. And then keep on, keep this all the way to the bottom. And you can see it here, the graph populated. If I want just half of the, say beginning with point B to no longer have a distributed load, I just delete it. And it updated the distributed load graph. All right. And then force, concentrated forces and moments. So I have one here. These are W has to, if W as shown, they act from upwards. So if you really want to make them acting downwards like we're used to, you need to put a negative. All right. Forces, concentrated forces, I could plot them. Look at the graph. Okay, let's go back. And then concentrated moments. You can have concentrated moments at some location. There's none here. And then the last red column, the one that you added, or you can add, you can edit everything, but it says edit what's in red only. So here, just to label locations along the beam to recognize them easier, point A, B, C, and D, and E, whatever. And then a moment of inertia. So you can have a moment of inertia that is same throughout, or you can have a moment of inertia that is changing. And here it shows like a half longitudinal section through the beam. So in case of a stepped shaft, do you follow? I'm wondering what you're doing. You're watching me on YouTube, or so the last column here is where you place the moment of inertia. And the graph, it shows you just the top half of a longitudinal section. Does it make sense? If I is the same throughout, no big deal. But if you have sections of different area moment of inertia, you verify against this graph and say, yeah, I have it's where the bearings go. This is a shoulder. There's a portion in between. Does it make sense? Okay. And everything else is done by, like what? In order to calculate. So calculates reaction of the support. You see them there by itself. And then plots shear force bending moment diagrams. And then I have the slope and I have the displacement. But you need to, for these problems, you need to reconcile with the end conditions. So in the y displacement diagram, you see red dots. I hope you follow. So red dots, you have to do this for some of the problems. Zekkers does not do stepped shafts or beams with different eyes, area moment of inertia along the beam. So, and actually there's a document that explains how to use the goal seek in Excel. But right now I'm pointing to you and the need for reconciling some constant integration. So really the way it goes, it just does successive integration. All right, so I get V by adding the concentrated forces and then integrating the distributed load. I get moment by integrating this. This is the in-between graph. It was in the book, and It will be similar graphs as I is a continuous constant value. Otherwise, there will be, the change in area moment of inertia, they will be visible here. And then the last two, so I integrate this to get slope, I integrate this to get y. But I need to reconcile the constant of integration, okay? And so let's see, it says solver data, solver data, solver data. I have slope at, initial at y, or at the support, I can change the support. It says, where is R1? It's at 0. I can change it to where the support does not coincide with the end of the beam. So full length in 9.58 feet, I can make the support at 1 foot inside. So diagrams changed. So this is where the support is. So I have overhang. I can move the other support further in. So I can make this like 8. And I can make this 2 to make it more dramatic. All right? Diagrams changed. But what I want to see, by adjusting these values, I want to see this point and this point moved on the horizontal axis. You can do trial and error, but you can spend the whole afternoon because you need to juggle with these two values until they get closer or on the y-axis. There is the solver. I mean, we can try. If I go back to the original configuration, that will make it a little bit easier. So I said this is 0. Come on, 0. Enter. Okay, this makes it easier. So y at 0 is already, I can make it 0. And then I can play with the initial slope by hand. So you can adjust the value by hand when it's this particular case was the first support coinciding with the left end of the beam. Otherwise, you need to play with both. So I already know that this flexion has to be 0 here. I need to play with the initial slope until this moves to 0. So let's see if we can do it by hand. Otherwise, the document that it's on the zip drive. Not on the zip drive, that you download together with the 2 spreadsheets, explains how to activate the solver. All right, so let's see if I'm changing this to only this much slope, the second red dot, does it go up or down? It moved up. Okay, so we've found the trend. Let's make it 5 or 4. It's getting closer. And you may have to help the solver, by the way. So in 3 steps, I've got it. It was pure luck. Again, it may not happen. But you can do it. You can use the solver, like I said. So let's see. And it's missing here. I need to upload it. There are the steps explained here. Instruction, beam deflection. So read this. Or you already read that as I was doing my my talk. So here it's showing how to add in the solver. All right, solver add in, and then it tells you how to run the solver. Okay, so you select these. The goal seeker is going to tune these values until the end value or the deflection at the other support goes to 0. Does it make sense? So what I did by hand was just one value because I knew the other one. Now the solver can do 2 at a time until I get the until I get the 2 deflections equal 0 by changing variable cells and set objectives. C9. Let's see what this C9. I think this is a residual. Yes. So the goal is to make this near 0 by adjusting these 2. What do you see here? They are the magnitude of the deflection at the one of the support and the other of the supports. Taken an absolute value, add them. If this is very small, it means that the 2 supports are on the x-axis. Does it make sense? So numerically, the solver, what it does, it manipulates these until the magnitude of this displacement and this displacement, I can alter, I can make it bad, looking bad again. So say 0.01, and this one going to, what was it, make it 9. 7, 9. Why it's not going to 0? Oh, I have radians, and this is a pretty tiny value. No. Maybe a bigger. I'm trying to alter it to where it's so 9. Okay. So this is in a bad arrangement. I don't have a slope. I know this has to be 0, yes, but it's not always obvious, or I cannot change it because this is at the end of the beam. If I have an overhang to the left, it cannot be 0. It was the case where I moved this to the right. It changed this to 0.1, I think, or 1. Anyway, so adjusting these two, the solver adjusts these two until the magnitude of this distance and magnitude of this distance taken together is very small. And what it does, okay? And it's all in line with successive integration that's described in your book. And that's why, you know, I prepared the spreadsheet, and I'm having you use it. You can save it, hold on to it. You can do other, you know, and for a capstone, or maybe as after you graduate. It's was verified with samples from the book and other books, so it's working. All right, so let's go back to don't say anything, don't say anything, don't save anything, and let's go to a piece of advice: start working on this early. It takes time, okay? So let's go to the problem. It says a white flange beam W1216 carries the load shown. Oh, never drew the figure, but we can do it. So in figure 7, figure 7 now. Yeah, so this is problem 9.7, and we have a support or simply supported beam with supports at the end, and then we have that symmetric loading. We saw that it's 3 feet, 10K. This is 8 feet, and then 10K, and this is 3 feet. All right, I have RA, I have R, I can call this B, C, and D. I think they have a name for the middle point, D equals. And we're going to use the formula method because we're asked to find the deflection of the load and at the center of the beam. The center of the beam is the maximum deflection. You go to appendix and go to formulas for simply supported beams, and our case is this one. Is that correct? So I'm on page, what page is this? 802, and our loading case is number C. So I'll print screen and take it to our paint and crop what we need. All right. Let me get a different marker. So we have a deflection at the loads. They call this point E. All right, so deflection of the loads, Y at B equals Y at C. And we make use of, so it's negative P times A over 6EI, 3L minus 4A. Okay. So what is P equal to? What is P equal to for our problem? So we need to match our problem with this appendix chart and information. So what is P? 10K. Are we going to use it as 10K? Now we go with 10,000 PSI. Or other pounds, I'm sorry. What is A equal to? We need to work with pound in inches, right? Pound inches in PSI. So what is A? What is A equal to? 3 feet converted to inches. So what is it? 36 inches. Okay, pounds. What is L? L is going to be 8 plus 6. That's 14 times 12. So 14 times 168. Yeah, 168. And this is, yeah, same 36. We take care of the denominator. So we're given the Y-plane steel beam. So it's a structural steel, right? If it's a Y-plane. So we need to get W for W 12 times 16 E or I first, I'm sorry, equals, and then for structural steel, E equals. All right, you got the back of the book, or appendices are, and so appendix, and we're looking at properties of structural steel, and it says American Institute of Steel Construction says use E as 29 times 10 to the power 6 psi. So taking care of this first, I said 29 times 10 to the power 6 psi. As for W, 12 by 16, it's what it is, 12 by 16, yes? So appendix, and we have hollow, square, rectangle, I shapes. 12, 16. So that is this one, right? So of the whole information here, we need I what? What value do we need? Let me see if you follow. You have the book in front of you. So we identified ours, W1216, and we are going to use the IX value. This is what goes here. So that's 103 inches at power 4. 103 inches at power 4. Was it clear? Okay. So I can return to Paint, and we can essentially complete this calculation. So it's going to be, I can add some values, just grab the calculator, punch the values in. So 3 times, I begin with the parenthesis, 3 times 168, negative 4 times 36 equals, took care of this. And then times 10 exponent 3 times 36 over 6 over 29 exponent 6 over 103 equals. And the value is, well, we have a minus. We put a minus here, indicative that they go down. Y is considered positive up. So this is Y, and this is X. Our Y is a negative 1, and it's 7.23 times 10 to negative 3 inches. This is the answer for deflection of the loads. Maximum deflection, it says also get it at the center, right? So that's maximum deflection. Y at E, which is Y max, is the